Well, it turns out I've been lying to you a little bit, just a little bit, and I guess it's time to come clean. You might remember this equation from one of the previous sections. This was hydrochloric acid mixed with water, and basically I said that the H and the Cl disconnected from each other, and they made H plus and Cl minus, and then the water was running around all by itself. That's not really what happens. What really happens is closer to this. If you mix hydrochloric acid with water, these two, the H plus and the Cl minus, do actually disconnect from each other. However, the Cl minus is still running around all alone, but the H plus actually attaches itself to the water, and it turns the water into H3O plus. And again, I want to emphasize that H3O plus is not water. The definition of water is H2O. This is something completely different. In fact, it's called a hydronium ion. Let me back up there. I thought that was going to pop up, but this material here is called hydronium ion. So in this case, the HCl actually donates its H plus to the water, and the water accepts the H plus from the HCl. Because of that, what you can say, and what many people do say, is that water, under these circumstances, is a base. Water is a base because it can accept H plus from HCl and turn itself into H3O plus. So, and here's the definition of what that particular molecule is. It's called a hydronium ion. So, originally I was showing you this equation up here, and I said, look, the H plus is floating around all by itself. In reality, when you dissolve an acid in water, pretty much the H pluses are, if there's nothing else to soak them up, they will be donated to water molecules, and they will turn the water molecules into H3O plus. So this bottom equation here that I'm circling is a more accurate representation of what's really happening when you dissolve an acid inside of a base. Now, most of the water molecules in your container, even if you pour an acid into them, most of them are still water molecules. There usually are not that many acid molecules compared to the water molecules. So even though many of the water molecules are converted into hydronium ions, almost all of the rest of the water molecules are just still water molecules running around all by themselves. But some of them are converted into H3O plus. So again, just to emphasize, this is the H plus donor, or the proton donor. This is the H plus acceptor, or the proton acceptor. So this is the base, in this case water, and this is the acid, HCl. So the punchline here, or one of the punchlines, in addition to pointing out that you can actually have H2O converted into something called H3O plus, the other punchline is that water can actually be a base, but it's only a base when it's in the presence of an acid. When it is in the presence of an acid, it can accept the proton from the acid. There's more lying, though. Here's a different lie, but it should be relatively simple. Relatively similar, I should say. So, again, I showed you this equation. Maybe in the previous section I said HCl mixed with ammonia, and the HCl, the H from the HCl gets donated to the ammonia, and it turns it into NH4 plus. However, when you actually dissolve ammonia in water all by itself, this is just pure ammonia and pure water mixed together. What will happen, it won't happen very often, but it will happen, is that the NH3 here will be converted into NH4 plus. So this ammonia over here had 3 H's, 3 hydrogens. This thing over here, the ammonium, has 4. Where did that extra hydrogen come from? Well, it actually comes from the water. Sometimes, at some low frequency, the water molecules will donate one of their H's, one of their H pluses, to the ammonia, and convert the ammonia, which I'm showing here, into ammonium. And because every once in a while some of the water molecules donate an H+, these water molecules that do the donating get turned into OH-. Because of that, the H2O under these circumstances isn't doing the accepting like I showed you on the previous slide. In this case, it's doing the donating of H pluses. This water molecule is donating an H plus or a proton to the ammonia. And the ammonia over here is doing the accepting. It's accepting an H plus from the water. And because the water over here is doing the donating, you say that the water is an acid and the ammonia is a base again. So, oh, and again, I mentioned this earlier, but the OH minus is called a hydroxide ion. So, strangely enough, on the previous slide I said that water can be a base. Under different circumstances, water can actually be an acid. It's not very good at this, but it does it a little bit. Water can be an acid, but only in the presence of a base. If water is in the presence of a base, it will donate, infrequently, but it will do it. It will donate protons to the base. The base will accept them, and basically this behaves like an acid, the water does, and the ammonia behaves like a base. So the punchline here, or the larger punchline, is that water can be an acid or a base. It stinks at doing both of those things, but it can do them a little bit. And whether it's an acid or a base depends on the situation the water finds itself in. If water is in the presence of an acid, then it behaves like a base. If water is in the presence of a base, then it behaves like an acid. I have a subtle point to make about acids and bases. Some of you may have noticed this, some of you may not have. My guess is that most of you probably have missed it, but it's a really subtle point. I said that an acid is a material that donates a proton, or donates an H+, and a base is a material that accepts H+ from an acid. So they're kind of opposites in that way. The subtle point is this: once the base is done accepting the H+, it actually turns itself, it actually becomes an acid, because once it's done accepting, it can actually donate the H+ back to whoever gave it the H+. So because the base can accept a proton, once it's accepted the proton, it becomes an acid. And conversely, once the acid donates the H+, it becomes a base because it can accept the H+ back again. So I'm going to, if that's a little bit confusing, I'm going to show that to you on the next slide, showing you an equation. Here, this is hydrochloric acid mixed with water, turns into chloride minus and hydronium ion. So over here, this was the H+ donor, because it had the H+, and it's going to donate it to the water. And this was the H+ acceptor. So, to point out to you, this is the acid, this is the base. However, once the HCl is done donating the H+ to the water, those materials on the left turn into the materials on the right. So the HCl over here turned into the Cl-. And hopefully you can see that there's no H+ that this thing can donate anymore. Because this thing can't donate H+'s anymore, but it can accept the H+. It could possibly accept one of the H's from the H3O+. It could the Cl- could accept one of the H+'s and turn back into this stuff. In other words, the reaction could run from right to left. Because this thing can accept, this is now a base. And because this thing can actually donate one of its H+'s to the chlorine, this hydronium ion is considered to be an acid. So just to try and drive this point home, the HCl over here is an H+ donor. But once it's done donating, it turns into Cl-. And the Cl- no longer can donate because it doesn't have an H+ to donate. But it can accept. Because it can accept, this turns into a base. The H2O actually accepts the H+ from the HCl. So this was a base, but once it's converted into H3O+, it is actually turned into an acid. And there are formal names for these types of acids and bases. This is the acid. It gets turned into Cl-. This thing here is called a conjugate base, and that's shown here. It's called a conjugate base because, well, it's called a base because it can accept an H+ from the H3O+. So that at least should make sense. It's called a conjugate base because it's conceptually tied or conceptually married to this molecule on the left side of the equation. That's why it's called a conjugate base. And the same thing for the water. This is a base, but once it's done accepting the H+ from the HCl, this water is not water anymore. It turns into H3O+. This stuff over here, the H3O+, can actually do some donating. It can donate H+'s back to the HCl. And because this thing can donate, it is an acid. And it's called a conjugate acid because conceptually this thing is tied or married to this other molecule over here on the left side of the arrow. So it can donate, so it's an acid, and it's connected in some way, at least sort of conceptually again, to this molecule on the left side of the arrow. They're related to each other, so it's called a conjugate acid. So again, this may seem a little bit weird. One of the points to point out here is that at least earlier in the course, many of the reactions that I've drawn have had the arrow going only in one direction, usually off to the right. However, it's important to realize in reality, chemical reactions can go either from left to right or from right to left, and sometimes they very frequently do both. So what I'm trying to point out here by the double-headed arrow is that the acid and the base on the left side can be converted into a base and an acid on the right side. And then there will be some back and forth. In other words, some of these things will be converted back into reactants, and some of the reactants will be converted back into products. But there are acids, conjugate bases, there are bases, conjugate acids. So here's an example that you can work on. You can pause the video at any point, but the idea is to look at this equation, find the acids and bases on the left side of the equation, and find the conjugate acids and bases on the right side of the equation. And you can pause and basically work on that on your own. So to deal with this, basically what you have to do is find the acids and bases on the left side. Well, I kind of highlighted it for you in red here, but in case it wasn't highlighted in red, you basically look at these two molecules and you figure out who was doing the donating of the H+. Well, this thing has an H attached to NO3, and then if you look on the right side of the equation, it's just NO3 without the H. So this thing must have donated its H+. Because it did the donating, this is the acid. This material over here, NO3-, has lost its H+, and it is no longer capable of donating any H+. Because of that, this is the conjugate base of this acid over here. Now, the water, then, just by the process of elimination, you can figure out that the water is the base. However, if you didn't want to do it by elimination, you could basically look at this and say, look, the water has 2 hydrogen atoms attached to it, but it gets turned into a hydronium ion, which has 3 hydrogen atoms attached. You started with 2 hydrogens, ended up with 3. This water molecule must have accepted this H+. Because the water molecule accepted the H+, this is behaving as the base on the left side of the equation. But it gets turned into a hydronium ion. The hydronium ion is actually capable of donating one of its H's back to the NO3-. Because it's capable of donating back, this is the acid. And in fact, it is the conjugate acid of the water molecule on the right side of the equation. So, just to summarize, this is the acid, this is its conjugate base. This is the base, this is its conjugate acid. So, just to emphasize what I want you to be able to do, if I show you an equation, like the one on the previous slide, where there's an acid and a base dissolved together, and I show you the products on the right side of the equation, you should be able to figure out who the acid is, who the base is, and what their conjugate acids and bases are. So that's the end of conjugate acids and bases, and that's the end of this section. We're going to talk about acidity and acid concentration in the next section.